Welcome back to Physics Fundamentals. In this video, I'm going to be introducing you to triangle trigonometry, which is the mathematician's way of saying the study of right angles. Specifically, the study of right angles inside of triangles for this lesson. So let me get my head out of the way. I'll remind you of some things that you may or may not have thought about in a while. The first one is the claim that two triangles are what we call similar if two pairs of angles have equal measure. So if I have triangle ABC and I have triangle XYZ, if I know that angle A and angle X have the same measure, and I know that angle B and angle Y have the same measure, that's all I need to know to say that these two triangles are similar. And in geometry, the idea of similar is same shape, different sizes. For two similar triangles, the lengths of corresponding sides are in proportion. So if on triangle ABC, I happen to know that this side is 1.5 centimeters and this side is 0.90 centimeters, and on triangle XYZ, the side over here is 23 centimeters, I can figure out that other side, because the corresponding sides, XY and YZ, let's call that extra side L for length. The ratio of those sides on that triangle has to be equal to the ratio of the same sides on the other triangle. And we can go through the algebra and solve from there. Right, the cross product test, 0.90L is going to be equal to 1.5 times 23, which my calculator tells me is 34.5. I'll round to two significant figures and call it 35. And then I'll get L by itself by dividing by 0.9. My calculator tells me that's 38.8 repeating, but again, two significant figures. I can solve from there. So that, at least in essence, should be something that you are vaguely familiar with. The idea of setting up a proportion between two triangles, and you may or may not have come across that angle-angle theorem, but it should make sense. If you know two sides of a triangle, three sides of a triangle add up to 180 degrees, so you know what the third side or the third angle is going to be. When it comes to trigonometry, working with right angles, well, all of a sudden we have half of the battle done for us. If I have a triangle that has a right angle, all I need to know is one additional angle out of the triangle. We generally label that one additional angle with the Greek letter theta. And this triangle will be similar to every other right triangle that has that angle theta. At some point in ancient past, mathematicians or geometers carefully constructed all of these triangles for various angles. Let's set the hypotenuse of the triangle as 1. And then we're going to name the other two sides sine and cosine. The names here are ancient Greek names that are completely taken out of context, so it's not worth knowing them as anything other than labels. But that's the idea. If you know the angle, then there is a prototype triangle whose hypotenuse, the side opposite the right angle, is 1, and the other sides are these measurements of sine and cosine. Another way of thinking about this, for my generic right triangle with angle theta, it has a hypotenuse. We're going to call it HYP for hypotenuse. The other two sides of a right triangle are called the legs. And for things like the Pythagorean theorem, you don't worry about which leg is which. But that's not where we are. So we are going to have to worry. We'll call one of the legs the opposite leg. It's the leg that's furthest away from the angle we know about. We'll call the other leg the adjacent leg. And so in general, the sine of theta over 1, the hypotenuse, is equal to the ratio of the opposite leg over the hypotenuse. And the cosine of theta over 1 is equal to the adjacent leg over the hypotenuse. And of course, dividing by 1 doesn't really do anything, so we can just get rid of that divide by 1 and write these formulas a little bit more cleanly. You will see as we go forward with our ideas here and working with triangles, that it's going to be useful to get the other possible ratio, right? Given 3 sides, there are 3 ways to combine them. The opposite and the hypotenuse, the adjacent and the hypotenuse, and the other way is the opposite and the adjacent. We call that other way the tangent. For quite some time, mathematics students and physics students and engineering students have memorized these 3 relationships by realizing that the abbreviation is pronounceable, right? If sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, you can actually sort of mostly pronounce SOHCAHTOA. Why someone decided that that was something pronounceable, I have no idea, but it was taught to me when I was in high school, and I can't get it out of my brain ever since. So now it is stuck in your brains as well. You're welcome. In days past, trigonometry was done using lookup tables. People would literally buy 100-page tomes that are just the value of sine, cosine, and tangent at various angles. We today, for the past 50 years, 40 years, um, calculators have been available that know these functions. So first of all, there are a couple of different ways you can measure an angle. We are going to be using degrees to measure our angle. So somewhere in your calculator, there is a menu where you can make sure that your calculator is in degree mode. I'm also going to go ahead and put it in normal mode instead of scientific notation, because I think that that's a little bit easier for probably most people watching this. And so, if I want to find the sine for the angle 37 degrees, I have a sine button built into my calculator. Every now and then you'll find a calculator where that's hidden, but it's usually pretty readily available. So sine 37 comes out as 0.6018, etc., etc. I'll just go ahead and evaluate the other ones. Cosine of 37 and tangent of 37. This is a great chance for you to double check and make sure that your calculator is in the proper mode. If your calculator is not in degree mode, you will be getting radically different results for those calculations. All right. So how do we use triangle trigonometry? Well, first of all, we need a triangle. That triangle needs to have a right angle, and that triangle needs to have some other angle that we know. Let's go ahead and make this a 42-degree angle. The last thing that we need is the length of one of the sides of the triangle. It doesn't matter which one, but we need one of them. I'm going to go ahead and give us this side right here. As 32.6 millimeters. The instructions for a problem like this might tell you to solve the triangle. Solve the triangle means that 3 pieces of information were given to you, and the other 3 pieces of information are unknown. In our case, the unknown is this angle. I'm going to call that angle phi, circle with a vertical line through it, as opposed to theta, circle with a horizontal line through it. These are the 2 Greek letters that are almost always used for representing angles. And then I've got 2 sides of my triangle. I'm going to call them little b and little c, just so I have some labels. The angle is the easiest part. You take 90 degrees, you subtract your known angle, and you get the other angle. Why 90 degrees? Well, the 3 angles of any triangle add up to 180 degrees, and when we're doing triangle trigonometry, we always have a right angle, which is taking up 90 of those degrees without thinking about it. So 90 degrees there, the other 90 degrees between the other 2 angles. But 90 degrees minus 42 degrees is 48 degrees. That is our unknown angle. Now we have to think about the 2 sides. And I'll start with side B. Right? Side B is touching the right angle, so it is a leg. It is not touching the 42-degree angle that we were given, so it must be the opposite leg. Side C is not touching the right angle, So it must be the hypotenuse. And then the given side is touching the right angle and also touching the angle we were given. So it must be the adjacent side. If I want to figure out side B, that means I'm looking for the opposite side. I know the adjacent side. And I know the trigonometric relationship, tangent of theta, is opposite over adjacent. Fill in the angle, 42 degrees. Fill in the length of the adjacent side, 32.6 millimeters. And instead of writing OPP, let's write the name that we gave this side, B. Rearranging that equation means that 32.6 millimeters times the tangent of 42 degrees is equal to B. And my calculator is very happy to calculate 32.6 times tangent of 42. And I get 29.3531, etc., etc., etc. 3 significant digits. 29.4 millimeters is the value I'll record for side B. Right. Get my calculator out of the way, and let's take a look at the other side. I've now taken care of the angle, I've taken care of B, I still have C left to deal with. C is the hypotenuse. The relationship between the hypotenuse and the adjacent side is cosine of theta. Cosine of theta is adjacent divided by hypotenuse. And then plug in. The adjacent side is given 32.6 millimeters. The hypotenuse C is unknown, and we notice here that the algebra is against us. But it's not that bad. First thing I'm going to do is multiply both sides of the equation by C so that I don't have a fraction anymore. This can be a little bit messy sometimes. The variable C and the function named cosine are right next to each other. Take care and be careful to make sure that you write them in a way that you can tell which is what. And then get C by itself by dividing by cosine of 42 degrees. All right, let's bring my calculator back onto the screen. And I can type in 32.6 divided by cosine of 42. My calculator tells me that the result here is 43.86, etc., etc. But again, 3 significant digits. So I'm going to round that and call it 43.9 millimeters. All right, so there we have it. There's the 2 unknown sides of the triangle solved using trigonometry. But what if that's not what you're given? What if instead of knowing the angle, all you know is sides? Let's go ahead and sketch out another right triangle. So we need to have a triangle. We need to know a right angle. And this time, let's say we have information about two sides and no information at all about the angles. Now I have a little bit more space to make notes around it. I need to choose an angle as my starting point. It doesn't really matter which one you choose, but I'm going to go ahead and choose this and call it angle theta. Once I've made that choice, I guess I can call the other one angle phi, and then I can think about the sides. Right? I'm not worried about phi, I'm really worried about theta. And compared to theta, well, I know the hypotenuse, it's the one that's not touching the right angle. And of the two legs, the one that's known is not touching angle theta, so it must be the opposite leg. And then the unknown must be the adjacent leg. Let's go ahead and call that A. The first thing I'm going to do is use the Pythagorean theorem to solve for the unknown side. The Pythagorean theorem is generally written in the form a squared plus b squared equals c squared, where a and b are the two legs. It doesn't matter which one is which, but I'm in the habit of always calling the adjacent leg a because a and adjacent start with the same thing, and the hypotenuse is always c. All right, grabbing out my calculator. 5.75 squared is 33.1 when I round it to three significant digits. And 7.25 squared is 52.6 when I round it to three significant digits. Subtract 33.1, I get that a squared is 19.5. Very conveniently, everything there was rounded to the nearest tenth. And then to get a by itself, I need to take the square root of 19.5. My calculator tells me that the square root of 19.5 is 4.42. My two lengths that were given were in centimeters, so I know that this one is going to be in centimeters as well. Now I need to know the angle. And so I'm looking at theta. And even though I know the adjacent side now that I've calculated it, it's a good habit to stick with the things that are given to you. That way, if you make a mistake, the mistake doesn't carry along for the rest of the problem. It's also a great way of double checking your work. I was given the opposite and the hypotenuse. The relationship between opposite and hypotenuse is sine. And yeah, I could divide that, but I'm going to leave it as that because it's going to actually make things easier on me. I also kind of dropped off the units. 5.25 is in centimeters, 7.25 is in centimeters. The centimeters between numerator and denominator have canceled each other out. This is actually a unitless quantity. Not only does your calculator have the trigonometric functions built in, it also has built-in inverse trigonometric functions. The inverse trigonometric functions are usually written as the name of the function raised to the negative first power, which is an odd notation. If you've gone far enough in the study of algebra, you've run across that as inverse function notation before. But that's what we're going to want to do, the inverse. So, grab my calculator, put it on the screen. On this calculator, the inverse sign is printed in the alternate text right above the sign button. So for this calculator, I hit the second key to get the alternate functions. Then I hit the sign key, and it's written as sine raised to the negative 1. Then I just type in my fraction. 5.25 over 7.25. And my calculator tells me that the angle here is 46.39, etc. I guess I'll round that to 3 significant digits and call it 46.4 degrees. Before I put this away, I did want to grab out one other calculator. I think I've mentioned before, I am not in any way, shape, or form sponsored by Texas Instruments, but I own a lot of Texas Instruments calculators because, well, they're the ones that I trusted when I was buying calculators 10 and 20 years ago. But this calculator is weird because it has sine and inverse sine on the same button. The way this calculator works, if I push the button once, it says sine. If I push the button a second time, it switches to the inverse sine. If I push it some more, it goes to these other things, the sinh and the inverse sinh function, using those as well beyond the scope of the course. Other than that, it works the same way. It gives me the same result. I just wanted to mention that that's another way that calculators can be built, so something you should be aware of. Anyway, now that we have that value, last thing we need is phi, which is still 90 degrees minus theta. Which in this case comes out as 43.6 degrees. There is a ton that you can do with triangle trigonometry and with trigonometry in general. This lesson is just barely scratching the surface. In the coming lessons, we will play around a little bit with one particular application that is of particular use in the study of physics, and then we'll have more that we can do going on from there. But for now, I think I've been talking long enough, so I'll wrap up with this. As always, thank you for joining me, and I'll see you in the next one.